The scale of the universe is beyond imagination, stretching across distances that challenge even the most sophisticated measuring tools. The observable universe extends roughly 46.5 billion light-years in every direction from Earth. This vast expanse is determined not simply by the age of the universe, 13.8 billion years since the Big Bang, but by the fact that space itself is stretching. As a result, light emitted billions of years ago has travelled through an expanding cosmos, making the actual distance to the farthest observable objects far greater than the light travel time alone. Even within this colossal sphere, we can detect a staggering diversity of structures, from small stars forming in stellar nurseries to immense galaxy superclusters spanning hundreds of millions of light years. Imagine a universe with boundary. What could exist beyond the known? Embark on a journey with us to explore the unseen expanses of space. Current estimates suggest that the observable universe contains around 2 trillion galaxies. This figure is derived from deep field surveys such as the Hubble Ultra Deep Field, HUDF, which captured light from galaxies that existed as far back as 13.2 billion years ago, and analyses by the James Webb Space Telescope, which has already identified galaxies at redshifts greater than 13. Each galaxy varies dramatically in size, mass, and stellar content. The Milky Way, for instance, stretches about 105,700 light-years across and hosts between 100 and 400 billion stars, alongside at least 100 billion planets, including those in its habitable zones. Its central supermassive black hole, Sagittarius A star, has a mass of roughly 3 million times that of the Sun, influencing stellar orbits across the galactic core. Yet the Milky Way is dwarfed by the giants of the universe. IC 1101, located approximately 1.04 billion light-years away in the Abell 2029 galaxy cluster, is currently the largest known galaxy. Its estimated diameter reaches 6 million light-years, nearly 60 times the span of the Milky Way. IC 1101's stellar mass is staggering around 100 trillion solar masses, dominated by a central black hole of immense proportion. Within such colossal galaxies, the sheer gravitational pull shapes not just stars, but entire clusters of neighboring galaxies, creating structures that echo the hierarchical complexity of the cosmos. The universe is also quantified in terms of mass-energy composition. The critical density required to determine the universe's curvature is roughly 9.47 times 10 negative 27 kilograms per cubic meter. Meanwhile, the total mass energy of the observable universe is estimated at 4 times 10, 69 kilograms, with ordinary matter accounting for only 5%. Dark matter, the invisible scaffold that governs galaxy rotation and cluster dynamics, constitutes approximately 27%, while dark energy, the mysterious force accelerating cosmic expansion, dominates 68% of the total content. These proportions shape both the large-scale structure and potential future of the universe. Distances in cosmology are often expressed in parsecs, with 1 parsec equivalent to about 3.26 light-years. Galaxies aggregate into clusters containing hundreds to thousands of members, which themselves form larger superclusters. Our own cosmic neighborhood resides within the Laniakea supercluster, encompassing around 520 million light-years and roughly 100,000 galaxies. This supercluster is interconnected by filaments of galaxies and intergalactic gas, stretching across tens of millions of light-years, while enormous voids regions virtually empty of galaxies can reach 300 million light-years across. Observational data from the Sloan Digital Sky Survey, which mapped over 930,000 galaxies across 1/3 of the sky, revealed the striking filamentary structure of the cosmic web, providing one of the first large-scale confirmations of theoretical predictions. Individual galaxies display their own layers of complexity. Stellar clusters, such as the Pleiades, located approximately 444 light-years from Earth, contain more than 1,000 stars tightly bound by gravity. Spiral arms, central bulges, and galactic bars define the structure of galaxies like the Milky Way, with central bulges containing roughly 10 billion stars. Interstellar space is not entirely empty. It contains diffuse gas, dust, and cosmic rays. But the intergalactic medium, IGM, between galaxies is even more tenuous. Averaging only 10 (-6) particles per cubic centimeter, the IGM forms a vast, nearly invisible framework for galaxy formation and large-scale structure. At the largest scales, the universe continues to surprise astronomers. Observations of high redshift galaxies at Z is greater than 10 show that complex structures were forming a mere 400 million years after the Big Bang. This means that within the first 3% of the universe's current age, star formation, galaxy assembly, and supermassive black hole formation were already underway. Galaxies were clustering, cosmic filaments were forming, and the earliest supernovae were seeding the interstellar medium with heavy elements, laying the foundations for future generations of stars and planets. Even in the voids, low-density regions stretch across hundreds of millions of light-years, punctuated by occasional dwarf galaxies and intergalactic clouds, creating a cosmic landscape of vast emptiness and dense clusters. The observable universe, though limited by the speed of light, represents only a fraction of the total cosmos. Beyond the edge of what we can see, light has not yet had time to reach us, and galaxies are receding faster than light due to cosmic expansion driven by dark energy. Current measurements suggest that the Hubble constant is approximately 67.4 kilometers per second per megaparsec based on Planck satellite data, while local measurements indicate a slightly higher value of 73.2 kilometers per second per megaparsec. This discrepancy, known as the Hubble tension, suggests there may be unknown physics governing the universe's expansion. Every discovery reveals new layers of complexity. Stars form in nebulae, with masses from a few solar masses to tens of thousands, while black holes span from a few solar masses to billions. Cosmic filaments, spanning tens to hundreds of millions of light-years, link galaxies and clusters, shaping the large-scale web of the universe. Even neutrinos, produced in the core of stars or during supernovae, traverse this vast expanse almost unhindered, carrying information about processes occurring billions of years ago. Interstellar magnetic fields, cosmic radiation, molecular clouds, dust lanes, stellar winds, and cosmic rays influence star formation, while galactic mergers, tidal interactions, accretion processes, and shock waves redistribute matter and energy across cosmic scales. The expanding universe. In the early 20th century, the prevailing belief among astronomers was that the universe was static, eternal, and unchanging, a vast cosmic stage where stars and nebulae drifted in perpetual calm. That perception was shattered in 1929 by Edwin Hubble, an American astronomer working at the Mount Wilson Observatory in California. Hubble focused his attention on distant spiral nebulae, now known as galaxies, using the 100-inch Hooker telescope, then the largest in the world. By analyzing their light spectra, he noticed a striking phenomenon. Nearly all distant galaxies exhibited redshift. Their light stretched toward the red end of the spectrum. The implications were staggering. Applying the Doppler principle, Hubble realized that these galaxies were moving away from Earth, and the farther the galaxy, the faster it receded. This observation formed the basis of what became Hubble's law, demonstrating that the universe itself was expanding. Hubble quantified this expansion by calculating a constant of proportionality, now known as the Hubble constant. Modern observations refine its value. The Planck satellite, analyzing the cosmic microwave background, estimates it at 67.4 kilometers per second per megaparsec, while local measurements from Cepheid variables and supernovae suggest a slightly higher value of 73. 2 kilometers per second per megaparsec, an unresolved discrepancy known as the Hubble tension. This constant indicates that for every 3.26 million light-years of distance, a galaxy recedes from us roughly 70 kilometers per second faster. Such movement is not caused by galaxies traveling through space. Rather, space itself is stretching, carrying galaxies along like dots on the surface of an inflating balloon. Each galaxy sees the same expansion, with no preferred center or edge. The recognition that space is expanding forced scientists to rethink the universe's origin. If space grows now, then in the past it must have been smaller, denser, and hotter. Tracing the expansion backward leads to a singular event, the Big Bang. This was not an explosion in space, but an expansion of space itself. During the first microseconds, temperatures exceeded 10 trillion Kelvin, and the universe was dominated by high-energy photons, quarks, and gluons. Protons, neutrons, and electrons coalesced within microseconds, forming the earliest atomic nuclei. At this time, the universe was opaque, with photons trapped in a dense plasma of charged particles, unable to travel freely. As the universe cooled, matter began to dominate over radiation, and gravity sculpted the first large-scale structures. Around 380,000 years after the Big Bang, the universe reached a temperature of about 3,000 Kelvin, allowing electrons to combine with protons and form neutral hydrogen. This decoupling of matter and radiation released photons, now observed as the cosmic microwave background CMB. Discovered serendipitously in 1965 by Arno Penzias and Robert Wilson at Bell Labs, the CMB measures 73 Kelvin, remarkably close to the 5 Kelvin predicted decades earlier by George Gamow, Ralph Alpha, and Robert Herman. Its uniformity, punctuated by minute fluctuations of 1 part in 100,000, provides a precise snapshot of the universe when it was just 0.003% of its current age, encoding information about early density variations that would evolve into galaxies, clusters, and superclusters. The expansion did not stop there. Astronomers using surveys such as the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, have mapped cosmic structures stretching hundreds of millions of light-years. Galaxies congregate in filaments, sheets, and nodes, separated by vast voids, often exceeding 300 million light-years across. The observable universe reveals an intricate cosmic web, demonstrating that matter is not evenly distributed, but concentrated along gravitational scaffolds. Clusters like the Virgo cluster, roughly 53 million light-years away, and the Coma cluster, 321 million light-years distant, illustrate hierarchical assembly with hundreds to thousands of galaxies bound together. Superclusters, such as Laniakea, containing approximately 100,000 galaxies, including the Milky Way, span over 500 million light-years, forming interconnected filaments and nodes across the cosmos. The acceleration of this expansion, discovered in 1998 through Type Ia supernova, observations by teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees, revealed the existence of a mysterious energy permeating space. This dark energy, constituting roughly 68% of the universe's total energy content, acts like a repulsive pressure, overcoming gravitational attraction at large scales. Ordinary matter represents only 5%, while dark matter, inferred from galaxy rotation curves and gravitational lensing, accounts for 27%. Dark energy causes galaxies outside our local gravitational group to recede faster over time, eventually moving beyond the limits of our observable universe. Simulations suggest that in 100 billion years, light from galaxies beyond the local group will no longer reach Earth, leaving only the Milky Way and its eventual merger with Andromeda visible to any remaining observers. The expanding universe also reshaped the understanding of time and space. Relativity, formulated by Albert Einstein in 1915, predicted that mass and energy could curve space-time, influencing cosmic expansion. Alexander Friedmann and Georges Lemaitre independently derived solutions to Einstein's equations, describing a dynamic universe capable of expansion or contraction. Observational confirmation by Hubble, combined with later precision measurements, solidified a cosmological model in which expansion is uniform, but the rate varies depending on dark energy, dark matter, and baryonic content. Redshift measurements now extend to galaxies at Z is greater than 10, observed by JWST, revealing that the earliest galaxies formed only 400 million years after the Big Bang. These nascent galaxies already contained hundreds of millions of stars and central black holes, with masses exceeding 100,000 solar masses, indicating rapid structure formation in the infant universe. Observations show there is no central point from which galaxies move away. Instead, every region of space experiences the same expansion. The universe may be infinite, with space stretching without bound, or it may have a global curvature that loops it back on itself. Data from distant supernovae, the CMB, and baryon acoustic oscillations help constrain cosmological models. Measurements of the Hubble constant, the density of matter, and the properties of dark energy provide ongoing information about the universe's expansion and structure. From Hubble's first observation to modern satellite surveys, studies of the expanding universe track its structure and growth over time. Galaxies, clusters, and voids provide evidence of expansion, enabling scientists to reconstruct cosmic history and observe ongoing changes in the cosmic web. The edge we can see every night. The sky above us is sprinkled with stars, each a distant furnace of light, some burning brightly, others already extinguished millions or even billions of years ago. When we gaze upward, we are not merely observing distance, we are peering into time. Light travels at a finite speed, roughly 299,792 kilometers per second. And the farther away an object lies, the longer its light has taken to reach us. This fundamental principle transforms the cosmos into a natural time machine, allowing us to observe events that occurred long before Earth even formed. The Sun, our closest star, delivers its light to Earth in just 8 minutes and 20 seconds. Beyond our solar system, light from Proxima Centauri, the nearest star to the Sun at 4.24 light-years away, reaches us only after more than 4 years of travel. The Andromeda Galaxy, our closest major galactic neighbour, located approximately 537 million light-years away, shines through time, its photons beginning their journey before humans even existed. In all cases, observing distant objects equates to observing the past, each photon carrying a story from a different epoch of cosmic history. Modern astronomy pushes this boundary further than ever. The Hubble Space Telescope, operational since 1990, has captured galaxies over 13 billion light-years away, such as GNZ 11, whose light was emitted when the universe was only 400 million years old, about 3% of its current age. In 2023, the James Webb Space Telescope revealed galaxies like GLASS Z13 and CES 93316, whose light began travelling toward us when the universe was a mere 300 million years old, an era known as the Cosmic Dawn. These discoveries provide unprecedented glimpses of galaxy formation in the earliest periods of cosmic history. This leads to the concept of the observable universe, the sphere of space from which light has had enough time to reach us since the Big Bang. Due to cosmic expansion, the farthest observable galaxies are not 13.8 billion light-years away, but roughly 46.5 billion light-years distant. This makes the observable universe a sphere about 93 billion light-years in diameter. Beyond this sphere, light has not yet reached us, and regions remain invisible, even though they likely contain countless galaxies and stars. This observable limit is not a physical boundary, but a horizon determined by the finite speed of light and the age of the cosmos. The farthest observable light originates from the cosmic microwave background, CMB, a faint glow permeating space, first detected in 1965 by Arno Penzias and Robert Wilson at Bell Labs. The CMB corresponds to radiation released when the universe cooled enough for protons and electrons to combine into neutral atoms, allowing photons to travel freely. Its temperature today averages 2.725 Kelvin, and satellites like COBE, WMAP, and Planck have mapped it with astonishing precision, revealing minute fluctuations of only a few millionths of a degree. These tiny irregularities represent the initial density variations that seeded galaxies, clusters, and cosmic filaments. The structure of the observable universe is complex. Galaxies cluster into groups, clusters, and superclusters, separated by immense voids, hundreds of millions of light-years across. The Sloan Digital Sky Survey has catalogued over 930,000 galaxies, revealing the cosmic web, a network of filaments stretching tens to hundreds of millions of light-years, threading through vast, nearly empty voids. These structures trace the gravitational growth of matter over billions of years, yet all of them lie within our observational horizon. Beyond that horizon, the universe may continue indefinitely, but we cannot see it because its light has not had time to reach us. As galaxies at the edge of the observable universe recede, their light is redshifted by enormous factors. Some of the most distant galaxies exhibit redshifts greater than 10, meaning their ultraviolet and visible light is stretched into infrared wavelengths. Instruments like JWST, with sensitivity to near and mid-infrared light, are essential for detecting these ancient galaxies, as the expansion of space shifts their emissions into bands invisible to optical telescopes. Even then, some regions remain unobservable because light emitted from there has not yet arrived, or may never reach us due to accelerated cosmic expansion driven by dark energy. This expansion implies a dynamic edge. As time progresses, galaxies that are currently visible will drift beyond our observational horizon, becoming undetectable. In roughly 100 billion years, distant clusters will recede faster than light can traverse the expanding space between, leaving only galaxies gravitationally bound to the Milky Way, such as the local group, visible. This reality underlines the distinction between the observable universe and the entire universe. The universe likely continues far beyond the 46.5 billion light-year radius, but no signal from those regions can currently reach us. The edge of the observable universe also demonstrates the principle of relativity in a cosmic context. Every point in space has its own horizon, forming a sphere of perception centered on that point. Were humans to observe the cosmos from a galaxy billions of light years away, we would perceive a different cosmic horizon, overlapping with ours but not identical. This symmetry reinforces the notion that there is no center to the universe, only a continually expanding space in which every observer experiences an equivalent, though distinct, observable volume. Mapping these extremes requires extraordinary precision. Redshift measurements, spectroscopic analyses, and infrared imaging allow astronomers to estimate distances with uncertainties as low as a few percent for the nearest galaxies and about 10–15% for the farthest ones. Cosmic surveys such as Cosmos and GOODS have provided detailed three-dimensional maps of galaxy distributions up to redshifts of 610, while JWST continues to push that limit further, observing galaxies formed in the first 200–400 million years post-Big Bang. These data allow cosmologists to model the growth of structure over cosmic time, test predictions of LCDM, lambda, cold dark matter, cosmology, and refine estimates of the Hubble constant. The edge we can see represents the limits of current observation. Beyond it lies a region that remains invisible, from which no light or information has yet arrived. The most distant galaxies act as cosmic messengers, but their signals are constrained by the laws of physics, cosmic expansion, and the finite speed of light. Observing these extremes presents technical challenges, requiring advanced telescopes and precise measurement techniques. The observable universe forms a sphere of both distance and time, tracing light from the infancy of the cosmos. Discoveries like GNZ 11 and CEERS 93316 reveal galaxies from the first few 100 million years, providing information about early structure formation. Beyond the observational horizon, regions remain unmeasured and unlit, leaving astronomers with data only from light that has reached us. The cosmic microwave background. Long before galaxies existed, the universe was a dense, opaque plasma of photons, electrons, and protons, with temperatures exceeding 3000 Kelvin. In this state, photons were trapped, repeatedly scattering off electrons. Only when electrons and protons combined into neutral hydrogen did the universe become transparent, allowing photons to travel freely. These photons persist today as the cosmic microwave background, CMB, the oldest observable light in the universe. In 1965, Arno Penzias and Robert Wilson were calibrating a highly sensitive horn antenna at Bell Laboratories in Holmdel, New Jersey, when they encountered a persistent, uniform hiss. The signal persisted regardless of direction, season, or local interference. After exhaustive checks, including removal of pigeons nesting in the antenna, they reached out to physicists at Princeton University, including Robert Dick and Jim Peebles. The physicists realized the signal corresponded to the predicted relic radiation of a hot, early universe. This accidental discovery confirmed decades of theoretical work and earned Penzias and Wilson the Nobel Prize in Physics in 1978. The CMB is remarkably uniform, just a few degrees above absolute zero, yet embedded within this uniformity are tiny fluctuations, 1 part in 100,000, which encode the seeds of all future structure. Denser regions in this early radiation field would collapse under gravity to form galaxies, clusters, and superclusters, while less dense regions expanded into vast cosmic voids. In essence, the CMB provides a snapshot of the universe at 380,000 years old, capturing the initial blueprint from which all large-scale structures emerged. Mapping the CMB has been a progressive journey. NASA's COBE, Cosmic Background Explorer, in 1989 first revealed the blackbody spectrum of the radiation, confirming the universe's hot origin. COBE's angular resolution was limited, but it demonstrated that the early cosmos was uniform to within 1 part in 1,000. In 2001, the Wilkinson Microwave Anisotropy Probe, DEWMAP, produced far more detailed maps, resolving fluctuations down to microkelvin scales. Finally, the European Space Agency's Planck satellite, launched in 2009, delivered the most precise full-sky CMB map, measuring temperature differences as small as 10 microkelvins. These maps reveal intricate patterns of hot and cold spots corresponding to density variations in the primordial plasma. From these patterns, cosmologists have extracted fundamental parameters of the universe with unprecedented precision. Current measurements indicate that the universe is composed of roughly 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. The Hubble constant, describing the current rate of cosmic expansion, is measured at 67.4 kilometers per second per megaparsec according to Planck, though local measurements using Cepheid variables suggest slightly higher values, highlighting ongoing debates in cosmology. The CMB also contains evidence of baryon acoustic oscillations pressure waves that propagated through the early plasma. These oscillations left subtle imprints in the distribution of matter, observable today as a characteristic separation between galaxies. Large-scale surveys such as the Sloan Digital Sky Survey (SDSS) and BOSS Baryon Oscillation Spectroscopic Survey have used these imprints to measure the expansion history of the universe and constrain models of dark energy. Beyond temperature variations, the CMB is polarized, exhibiting faint twisting patterns in the orientation of photons. Polarization arises from photons scattering off electrons in a slightly anisotropic radiation field, producing E-mode and B-mode patterns. Detecting primordial B-modes could provide direct evidence of gravitational waves generated during cosmic inflation, the hypothesized exponential expansion of space during the first trillionth of a second after the Big Bang. Experiments like BICEP-2, the South Pole Telescope, and Simon's Observatory are at the forefront of this search, probing fluctuations at the level of 1 part in 10 million. The CMB is effectively a spherical shell around us, about 46 billion light-years away in every direction. Photons from earlier times could not travel freely because the universe was opaque before recombination. Due to the expansion of space, these photons have been stretched from visible and ultraviolet wavelengths into the microwave range, with typical wavelengths now around 1.9 millimeters. Every observer in the cosmos sees their own CMB sphere, illustrating that the cosmic horizon is relative. There is no absolute center of the universe, only a network of overlapping observable volumes. Beyond its uniformity, the CMB exhibits anomalies. The CMB cold spot, first detected by WMAP and confirmed by Planck, is an unusually large region, slightly cooler than its surroundings. Its origin remains debated. Some suggest a supervoid, others propose quantum fluctuations or features from beyond the observable universe. Additionally, a small hemispherical power asymmetry hints that the early universe may not have been perfectly isotropic. These features remind us that even in a remarkably uniform cosmos, subtle irregularities can provide clues about physics at the highest energies. The CMB provides data about the early universe. Its temperature fluctuations and polarization allow scientists to reconstruct conditions during the first 380,000 years, measure the universe's expansion, and constrain the properties of dark matter and dark energy. Observations indicate the universe is flat on large scales, consistent with predictions from inflation. Some portion of the static on an old analog television screen included signals from the CMB, accounting for roughly 1% of the noise. Today, sensitive instruments continue to measure the CMB from ground-based observatories in Chile, Antarctica, and the Atacama Desert, as well as from space missions. Each measurement of photon properties and temperature fluctuations contributes to mapping the early universe. The cosmic microwave background represents the earliest light capable of reaching us, marking the transition from an opaque plasma to a transparent universe. Beyond this boundary lies a period before stars and galaxies formed that remains unobservable. Analysis of the CMB provides information about the density, temperature, and distribution of matter at this early stage, informing models of cosmic evolution and large-scale structure formation. The CMB marks the observable limit of the early universe. Its temperature and polarization patterns provide information about conditions, including density fluctuations and anisotropies. Observations of these features help scientists study the universe's evolution and constrain models of cosmic inflation and structure formation. Is space flat or curved? For much of human history, space was considered a static, empty background through which stars and planets moved in accordance with Newton's laws. This perception changed dramatically in 1915 when Albert Einstein published his general theory of relativity, revealing that space and time form a dynamic fabric known as spacetime, which bends in response to mass and energy. Gravity, proposed by Einstein, is not a force acting at a distance, but the curvature of spacetime itself. Planets orbit stars not because they are pulled, but because the paths they follow are curved by the geometry of space around massive objects. If spacetime curves around stars and planets, it is reasonable to investigate the global curvature of the universe. Cosmologists identify three possibilities: flat, positively curved, like a sphere, or negatively curved, like a saddle. Each geometry affects the paths of galaxies and light. Einstein's equations indicated that the universe's shape depends on its total energy density, which includes ordinary matter, dark matter, radiation, and dark energy. In the early 20th century, astronomers such as Vesto Slipher and Edwin Hubble mapped galaxy motions, discovering that the universe is expanding. However, expansion alone does not reveal geometry. A cosmic ruler was needed, something of known size across billions of light years. That ruler came from the cosmic microwave background, CMB. The tiny fluctuations in the CMB's temperature serve as standard rulers because their apparent angular size depends on the curvature of space. In a positively curved universe, these spots would appear larger than expected. In a negatively curved universe, they would appear smaller. By precisely measuring the spacing and scale of these fluctuations, cosmologists can infer the total energy density of the universe, distinguish between contributions from dark matter, dark energy, and ordinary matter, and test predictions from the inflationary model that describe the early, rapid expansion of space. NASA's COBE satellite, launched in 1989, produced the first detailed full-sky maps of the CMB, confirming its uniformity but lacking the resolution to measure small fluctuations. WMAP, launched in 2001, mapped temperature variations with microkelvin precision, providing the first robust constraints on cosmic curvature. These measurements suggested the universe is astonishingly close to flat, with deviations from perfect flatness less than 1%. The Planck satellite, launched in 2009 by the European Space Agency, refined these measurements further. Its 2018 data release indicated that the curvature parameter, omega, is consistent with 0 to within 1 part in 10,000, effectively flat on the largest observable scales. Planck also measured the polarization of the CMB, detected subtle anisotropies, and provided improved estimates of key cosmological parameters such as the Hubble constant, baryon density, and dark matter fraction, offering a more complete picture of the universe's composition, evolution, and early inflationary history. Inflation theory proposes that in the first trillionth of a second after the Big Bang, the universe expanded exponentially. This expansion would have stretched any initial curvature, making the observable patch of the universe appear flat. Inflation also explains the uniformity of the CMB while preserving tiny fluctuations that seeded galaxies. Inflation also explains the uniformity of the CMB across the sky, smoothing out irregularities while leaving the tiny fluctuations that seeded galaxies. Despite precise measurements, subtle anomalies persist. Both WMAP and Planck detected the cold spot and other large-scale irregularities in the CMB. Some analysts suggest a slight positive curvature, while others attribute these features to statistical fluctuations or local structures such as supervoids. The geometry of space also dictates cosmic destiny. In a flat universe, expansion continues indefinitely, gradually slowed by gravity, but eventually dominated by dark energy, which drives acceleration. A positively curved universe could eventually halt expansion and collapse in a big crunch, though current observations of accelerated expansion make this scenario unlikely. A negatively curved universe would expand forever at an ever-increasing rate, with galaxies receding toward cosmic isolation. The fate of all structures, from stars to clusters, is intimately linked to the universe's shape. In a perfectly flat universe, the total energy could sum to 0, the positive energy of matter and radiation balanced by the negative energy of gravity. This balance is consistent with models in which the universe emerged from a small, hot, dense state and expanded to its current size. Observational evidence beyond the CMB supports flatness. Baryon acoustic oscillations, BAO, observed in galaxy surveys such as SDSS and BOSS, match predictions for a flat universe. Type Ia supernova surveys, measuring the expansion of space over billions of years, corroborate a flat cosmology dominated by dark energy. Gravitational lensing studies, including those from the Dark Energy Survey, map the distribution of dark matter and confirm a homogeneous, flat structure on the largest scales. Collectively, these observations reinforce the conclusion drawn from CMB measurements. Space is astonishingly flat within the observable universe. However, the observable universe is only a fraction of what may exist. Beyond the cosmic horizon, space could possess subtle curvature undetectable from our vantage point. It could even loop back on itself, forming a finite but unbounded universe, analogous to a three-dimensional hypersphere. While such structures remain beyond observational reach, their theoretical possibility underscores the limits of cosmology. We can only measure what light has reached us. The study of cosmic curvature exemplifies the interplay between theory and observation. Einstein predicted that space-time could bend, inflationary models suggested extreme flatness, and high-precision measurements, from Kobe to Planck, confirmed these predictions to remarkable accuracy. Geometry is not abstract mathematics, it is encoded in the motion of galaxies, the flow of time, and the evolution of cosmic structure, the shape of everything. When we gaze into the deep night sky, we see galaxies arranged not at random but woven into a delicate architecture, strands of light stretching across the cosmos like a vast, three-dimensional web. Clusters gather into nodes where filaments intersect, while immense voids, hundreds of millions of light-years across, open like cosmic caverns between them. Yet even this grand pattern, the cosmic web, represents only a fraction of what defines the universe's true form. To grasp the shape of everything, we must look beyond the visible and imagine the geometry of space itself, the invisible scaffold that determines how galaxies move, how light bends, and how reality is structured on the largest conceivable scales. Einstein's general relativity tells us that space can be flat, positively curved, or negatively curved, but geometry alone doesn't capture the universe's full complexity. Beyond curvature lies topology, the study of how space is connected, folded, or looped back upon itself. Curvature describes local geometry, while topology defines global structure. Whether the universe is infinite or finite, whether it has edges or wraps around like the surface of a torus. Locally, space could appear flat, but globally, it might be curved in ways that cause a traveller moving far enough in one direction to eventually return to their starting point. The universe could therefore be finite, but unbounded, much like a higher dimensional analogue of Earth's surface, where straight lines eventually meet. To investigate this possibility, cosmologists turn to the cosmic microwave background, CMB. If the cosmos loops back on itself, light from the same region could circle the universe multiple times, producing repeating patterns in the CMB. Researchers have searched for these matched circles, pairs of identical temperature fluctuations appearing in different parts of the sky. The Planck satellite, launched in 2009, and data from WMAP before it, found no conclusive repetition. This absence implies that if the universe does wrap around, its scale must be at least 10 times larger than our observable horizon, meaning the full universe, whatever its shape, is vastly beyond what we can see. The observable universe, about 93 billion light-years across, is bounded not by physical walls, but by time itself. Light from beyond that distance simply hasn't had long enough to reach us since the Big Bang. The metric expansion of space, described by the Friedmann-Lemaitre-Robertson-Walker FLRW metric, continually stretches the distances between galaxies. This means that while the observable sphere defines the limits of what we can detect, it likely encloses only a minuscule portion of all existence. Some cosmological models, especially those involving eternal inflation, propose that space extends indefinitely, forming a multiverse, an endless mosaic of bubble universes, each with its own geometry, density, and even physical constants. In some regions, gravity or electromagnetism might behave differently. In others, atoms might not form at all. Back within our own cosmic bubble, observations reveal a surprising order. On scales larger than 100 million light-years, the distribution of matter becomes statistically uniform. Surveys such as the Sloan Digital Sky Survey, SDSS, 2DF Galaxy Redshift Survey, and Dark Energy Spectroscopic Instrument, DESI, have mapped the positions of millions of galaxies, confirming that the universe obeys the cosmological principle. It appears isotropic and homogeneous on grand scales. Yet within that apparent uniformity, quantum fluctuations from the universe's earliest moments have grown into galaxies, clusters, and vast filaments. These patterns, visible both in the CMB and in large-scale galaxy surveys, encode the initial conditions of cosmic evolution and hint at the underlying geometry of space itself. The universe's shape directly influences its destiny. A positively curved universe, with total density exceeding the critical value, could eventually halt its expansion and contract in a cataclysmic Big Crunch. A negatively curved universe would expand forever, with galaxies receding beyond each other's horizons. A perfectly flat universe expands indefinitely, but at a rate moderated by its energy components. Current observations including Type Ia supernova surveys, baryon acoustic oscillations, and CMB measurements point to a flat geometry dominated by dark energy. In this model, space itself is not static. It stretches faster and faster, accelerating the cosmic expansion. This acceleration has extraordinary consequences. In roughly 100 billion years, galaxies beyond our local group, including Andromeda and the Milky Way, which will have merged by then, will fade from view, redshifted beyond detectability. The observable universe will shrink, not in size, but in content, leaving only nearby galaxies visible as the universe continues expanding and cooling. Topology and curvature are not just mathematical abstractions, they affect real, measurable phenomena. Light traveling through a positively curved universe focuses slightly, while in a negatively curved one, it diverges. Astronomers use gravitational lensing, the bending of light by massive structures, to constrain the universe's geometry. Observations from the Hubble Space Telescope, the Dark Energy Survey, and Euclid, launched in 2023, have measured the shapes of millions of distant galaxies, confirming that space is flat to within 1 part in 10,000. Yet, small anomalies in the CMB, including the cold spot, the axis of evil, and hemispherical asymmetries, continue to intrigue researchers. Some suggest these features could be imprints of regions beyond our observable horizon, or even signatures of topological complexity in the global structure of space. The next generation of missions aims to probe these mysteries more deeply. Japan's Lightbird satellite, planned for launch in the 2030 seconds, will measure the CMB's polarization with unprecedented precision, searching for the subtle B-mode patterns caused by primordial gravitational waves. Ground-based observatories such as CMBS-4 and space telescopes like Euclid and Nancy Grace Roman will refine our maps of structure formation, dark energy, and cosmic geometry. These instruments may not only test inflation and curvature, but also reveal whether space itself has a non-trivial topology, perhaps finite, connected, or looping in ways still unimaginable. The shape of everything also intersects with the most fundamental scales of physics. Quantum mechanics and general relativity, when combined, predict that space-time may not be smooth, but quantized at the Planck length 1.616 times 10 to the power of negative 35 meters. At that scale, the very concept of geometry could break down, replaced by discrete quanta of space. Theories such as loop quantum gravity and string theory attempt to describe this microscopic structure, proposing that space-time may emerge from more fundamental elements or even hidden dimensions curled up on subatomic scales. If these theories are correct, the universe's large-scale shape may reflect properties of an underlying higher dimensional structure described by quantum gravity models. Exploring the universe's shape allows scientists to investigate the geometric and physical principles that govern space, matter, and energy. The curvature and topology of space determine how matter clusters, how light moves, and how time evolves. Even if the universe extends infinitely, our observations are limited by the reach of light. The observable universe, a sphere with a radius of 46.5 billion light-years, defines the boundary of what can currently be measured. Beyond it may exist regions with different curvatures or physical laws, still beyond observational reach. What does an edge even mean? When people imagine the edge of the universe, it's tempting to picture a cosmic wall, a barrier where space stops and everything simply ends. But in cosmology, the term edge doesn't mean a border you can reach or cross. Instead, it refers to a limit in what can be observed, measured, or causally connected. The universe doesn't appear to have an edge like a planet or an object. It has horizons that define how far information, matter, and light can travel within the age of the cosmos. Examining the idea of this edge involves studying how space, time, and expansion behave on cosmic scales. The observable universe has a measurable size of roughly 93 billion light-years across. That figure might sound like a physical boundary, but it's not. It's determined by the distance that light has been able to travel since the Big Bang. Because space itself has been expanding during that time, light from the earliest moments has stretched along with it, giving rise to the enormous radius we measure today, about 46.5 billion light-years in every direction. What lies beyond that radius is not empty or non-existent. It's simply unobservable because its light hasn't had enough time to reach us. The term edge becomes even more complex when considering that the universe is not expanding into anything. There is no external space beyond the cosmos. Rather, the expansion occurs within space itself. Galaxies are not moving through space away from one another. They are being carried apart as the fabric of space stretches. This means that even if you could somehow travel 46.5 billion light-years outward, you wouldn't reach a wall or an end. You'd encounter more galaxies and regions of space exhibiting the same physical behavior. One of the most precise ways to define this boundary is through what cosmologists call the particle horizon. This represents the farthest distance from which particles of light photons could have traveled to reach us since the beginning of the universe. Everything within this horizon is causally connected, meaning it could have influenced or been influenced by events that eventually reached us. Everything beyond that limit is causally disconnected. Current models suggest that the total universe could be hundreds or even trillions of times larger than the observable portion, possibly infinite. Einstein's general theory of relativity provides the mathematical foundation for these ideas. The equations describe how space-time curves in response to mass and energy, forming a dynamic structure rather than a static container. This means that the universe's geometry, whether it's flat, open, or closed, dictates how we interpret its boundaries. Measurements from the Planck satellite in 2018, which analyzed the cosmic microwave background with extraordinary precision, indicate that the universe is flat to within a 0.4% margin of error. A flat universe doesn't have an edge. It extends endlessly unless topology imposes a repeating pattern, such as a three-dimensional torus, where traveling far enough in one direction could bring you back to your starting point. If space is curved positively, like the surface of a four-dimensional sphere, then the universe could be finite, yet unbounded. In that case, the edge would not be a border, but a return point, a loop through higher dimensional geometry. A negatively curved, open universe would be infinite, expanding forever, and without any boundary at all. These scenarios describe different geometric interpretations of what edge could signify in cosmology. Cosmic expansion adds another layer to this concept. Edwin Hubble's observations in 1929 revealed that galaxies are receding from us at speeds proportional to their distance, a relationship expressed as v equals h0d, where h0 is the Hubble constant. Recent measurements estimate this value at around 70 kilometers per second per megaparsec. Although slight differences exist between methods, Planck data suggest closer to 67.4. while the SH0ES project finds around 73. This expansion means that more distant regions are moving away faster, and beyond a certain distance, space is receding faster than light. Those regions form the universe's cosmic event horizon, a practical boundary beyond which no future signals can ever reach us, no matter how long we wait. To visualize this, consider that any galaxy more than about 16 billion parsecs, or roughly 52 billion light-years away, is already moving out of causal contact. Light it emits today will never reach Earth because the expansion of space between us outpaces the speed of light itself. This horizon grows as time passes, swallowing more galaxies from view, even though they still exist in the greater universe. The edge of what we can see is thus a moving target dictated by the expansion rate, not a static border. Astronomers use the cosmic microwave background relic radiation from when the universe was just 380,000 years old to study conditions at the observable edge. Its uniform temperature shows how far photons have travelled from that early epoch. Yet the CMB isn't the edge of space, it's the limit of transparency. Before that time, the universe was a dense plasma where light couldn't travel freely. The photons we detect today have been stretched by cosmic expansion, carrying information about the boundary between the visible and the unobservable. Theoretical physics introduces even deeper ways to think about edges. In inflationary cosmology, the universe underwent exponential expansion less than 10, -32 seconds after the Big Bang, enlarging microscopic quantum fluctuations to cosmic scales. That inflation likely produced regions so far apart that they can never communicate with one another, even at the speed of light. Each region could have slightly different densities, energies, or even physical constants, forming a multiverse of independent bubbles. Black holes demonstrate similar boundaries in miniature. The event horizon surrounding a black hole marks the point beyond which not even light can escape the gravitational pull. In cosmology, the universe's event horizon serves a comparable role, defining a region of no return for light and matter relative to any observer. These analogies help scientists frame cosmic limits using principles observed in more localized extreme environments. Galaxies, clusters, and superclusters. Across the observable universe, matter is organized into a hierarchy of vast structures, galaxies, clusters, and superclusters that form the large-scale framework of the cosmos. These immense systems are not randomly arranged, but interconnected through filaments of dark matter and gas, forming what scientists call the cosmic web. This web-like pattern extends across hundreds of millions of light-years, shaping the visible universe and revealing how matter is distributed on cosmic scales. Galaxies are the fundamental units of cosmic structure. Each one is a vast, gravitationally bound system composed of stars, gas, dust, and dark matter. The Milky Way, our home galaxy, spans about 100,000 light-years in diameter and contains approximately 200 to 400 billion stars, along with an estimated 100 billion planets. Observations from the Hubble Space Telescope and, more recently, the James Webb Space Telescope, JWST, indicate that there are likely around 2 trillion galaxies within the observable universe. JWST's infrared observations have identified galaxies that existed less than 300 million years after the Big Bang, showing that galaxy formation began very early in cosmic history. Galaxies exhibit a variety of shapes and compositions. Spiral galaxies, such as the Milky Way and Andromeda, have flattened disks with spiral arms rich in young stars and gas, while elliptical galaxies, such as Messier, 87 inches the Virgo cluster, are more spherical and contain older stellar populations. Irregular galaxies lack distinct shapes, often forming through gravitational interactions or mergers. Messier 87, for example, contains a supermassive black hole about 6.5 billion times the mass of the Sunday. The black hole's shadow was imaged by the Event Horizon Telescope in 2019, providing direct evidence of black holes as central components of galactic structure. Galaxies rarely exist in isolation. They tend to cluster together under the influence of gravity. A galaxy cluster can contain anywhere from a few dozen to several thousand galaxies, as well as large amounts of hot gas and dark matter. The Virgo cluster, located about 54 million light-years away, contains over 1,300 catalogued galaxies. The Coma cluster, another massive structure, contains more than 1,000 galaxies within a region roughly 20 million light-years across. Studies show that visible matter, stars and gas accounts for only about 15% of a cluster's total mass. The remaining 85% is made up of dark matter, which can be detected through its gravitational effects, particularly via gravitational lensing. Clusters of galaxies are themselves part of larger formations known as superclusters. These are enormous networks of galaxy clusters and groups that can extend for hundreds of millions of light-years. The Milky Way belongs to the Local Group, a collection of about 54 galaxies that includes Andromeda, M31, Triangulum, M33, and numerous dwarf galaxies. The Local Group is situated within the Virgo supercluster, a structure approximately 110 million light-years across. In 2014, astronomers using data from the Sloan Digital Sky Survey identified that the Virgo supercluster is part of an even larger structure known as Laniakea, meaning immense heaven in Hawaiian. Laniakea stretches across about 520 million light-years and contains roughly 100,000 galaxies, with a total mass equivalent to 100 quadrillion suns. These immense collections of matter are interconnected by cosmic filaments, vast bridges of dark matter and gas that define the large-scale structure of the universe. Between these filaments are enormous empty regions called voids. The Sloan Digital Sky Survey, SDSS, has mapped millions of galaxies, revealing a web-like pattern of filaments, walls, and voids extending across billions of light-years. One of the largest known structures, the Hercules Corona Borealis Great Wall, discovered in 2013, spans nearly 10 billion light-years, 1/10 the diameter of the observable universe. Its immense scale provides insight into how matter is distributed on the universe's largest scales. Cosmic voids are equally important in understanding large-scale structure. The Bootes void, discovered in 1981, measures about 330 million light-years across and contains fewer than 60 galaxies, where thousands would be expected. Although these regions appear empty, they contain sparse amounts of hydrogen gas, dark matter, and cosmic background radiation. Voids play a crucial role in mapping cosmic density variations and in testing models of cosmic inflation and dark energy. The study of the most distant galaxies provides insight into how structure evolved near the cosmic edge. The galaxy GN-Z11, discovered in 2016 using the Hubble Space Telescope, lies 13.4 billion light-years away, and its light originated when the universe was only about 400 million years old. Observations from JWST have detected even earlier candidates, potentially formed just 250 million years after the Big Bang. These discoveries help researchers investigate the epoch of reionization, a critical phase when the first stars and galaxies ionized hydrogen in the early universe, making it transparent to light. Galaxy clusters also serve as natural laboratories for studying high-energy phenomena. The Bullet cluster, located 3.7 billion light-years away, is one of the most well-studied examples. It formed through the collision of two galaxy clusters, moving at speeds exceeding 4,500 kilometers per second. X-ray observations from the Chandra Observatory reveal that the visible gas has been displaced from the bulk of the cluster's mass, which remains aligned with dark matter detected through gravitational lensing. This separation provides some of the strongest evidence for the existence of dark matter. Supermassive black holes, located at the centers of galaxies, influence both their host galaxies and their environments. The galaxy M87, for instance, produces jets of relativistic particles, extending thousands of light-years into intergalactic space. These jets heat the surrounding gas and regulate star formation, influencing how galaxies evolve over time. In galaxy clusters, the combined activity of thousands of galaxies and black holes produces halos of hot plasma with temperatures reaching tens of millions of Kelvin. This gas emits X-rays that can be detected by space observatories like Chandra and XMM Newton. The large-scale distribution of galaxies provides critical evidence about the composition and evolution of the universe. The European Space Agency's Euclid mission, launched in 2023, aims to map billions of galaxies across more than one-third of the sky, reaching back 10 billion years. By measuring how galaxies cluster and how light bends due to gravity, Euclid will refine our understanding of dark matter, dark energy, and the universe's overall geometry. Similarly, surveys such as the Dark Energy Spectroscopic Instrument, DESI, and the Legacy Survey of Space and Time, LSST, at the Vera C. Rubin Observatory will chart the positions of tens of millions of galaxies, producing the most detailed, three-dimensional maps of the cosmos ever created, cosmic voids, and the web of space. The universe, observed on its largest scales, resembles a colossal three-dimensional web, a complex lattice of filaments, nodes, and enormous voids stretching across billions of light-years. This cosmic web is the framework upon which galaxies, clusters, and superclusters are arrayed. Its origin lies in minute quantum fluctuations during the inflationary epoch, amplified by gravitational attraction over 13.8 billion years. Dense regions accumulated matter, forming filaments and clusters, while underdense regions expanded more rapidly, producing vast cosmic voids. These voids, often hundreds of millions of light-years across, are not simply empty space. They are dynamic regions that reveal critical information about dark matter, dark energy, and the evolution of large-scale structures. Cosmic voids vary in size and density. The Boötes void, discovered in 1981, spans roughly 330 million light-years in diameter and contains only about 60 galaxies. A stark contrast to the thousands expected in a uniformly distributed volume. The Eridanus supervoid, associated with the cold spot in the cosmic microwave background, extends nearly 1 billion light-years, making it one of the largest underdense regions ever observed. The local void, beginning near the Milky Way's local group, stretches over 150 million light-years and contributes to the peculiar velocities of nearby galaxies, accelerating them toward denser structures. Even these seemingly empty spaces contain low-density gas and dark matter. Observations using Lyman alpha absorption lines indicate that 10–20% of baryonic matter in the universe resides in voids, tracing the remnants of primordial conditions. Inside voids, expansion is faster than the average Hubble flow due to underdensity. Galaxies within these voids evolve differently from those in filaments or clusters, generally appearing smaller, less massive, and slower to form stars. The Void Galaxy Survey, conducted between 2008 and 2012, catalogued over 1,000 galaxies in void interiors, revealing low metallicity and simpler structures compared to cluster galaxies. Hydrogen gas in these regions maintains temperatures around 10,000–20,000 Kelvin, detectable via ultraviolet and radio observations. In some of the largest voids, such as the Sculptor void, gas densities drop to less than 1/10 the average cosmic density, yet the gravitational influence of surrounding filaments continues to subtly shape the motion of galaxies within. Filaments form the connective tissue of the cosmic web, channeling galaxies, gas, and dark matter toward dense nodes. The Hercules Corona Borealis Great Wall, spanning approximately 10 billion light-years, exemplifies the immense scale of these structures. Clusters of galaxies embedded within filaments, such as the Coma cluster, located 330 million light-years away, contain over 1,000 galaxies and a total mass exceeding 1.3 times 10^15 solar masses. The Perseus cluster hosts intra-cluster gas heated to 50 million Kelvin, emitting intense X-rays observed by telescopes like Chandra and XMM Newton. These filaments are composed predominantly of dark matter, with baryonic matter forming only 15–20% of the total mass. Yet their influence is immense, guiding the growth and motion of clusters and surrounding voids. The relationship between voids and filaments is reciprocal. Galaxies on void peripheries migrate along filaments toward denser nodes, while void interiors remain relatively undisturbed. Observations of the Eridanus supervoid indicate that photons traveling through it experience slight redshifts due to the integrated Sachs-Wolf effect, offering indirect evidence of large-scale underdensities. Baryon acoustic oscillations, residual ripples from the early universe, imprinted on the cosmic microwave background, extend across both filaments and voids, serving as a cosmic ruler to measure distances and map the universe's expansion. Clusters and superclusters are the nodes where filaments converge. The Shapley supercluster, located 650 million light-years away, contains over 8,000 galaxies and a total mass exceeding 5 times 10^16 solar masses. Its gravitational influence extends over hundreds of millions of light-years, affecting the motion of surrounding voids and filaments. The Sloan Great Wall, discovered in 2003, stretches more than 1.37 billion light-years, containing clusters and groups with combined masses exceeding 10^17 solar masses. Observations combining optical imaging, X-ray measurements, and gravitational lensing have revealed the distribution of both visible and dark matter in these structures, showing that dark matter dominates their mass, accounting for roughly 80–85% of the total. The filaments connecting clusters also host a significant fraction of the universe's missing baryonic matter. Observations with Chandra and XMM Newton have detected hot intergalactic gas with temperatures ranging from 10⁶ to 10⁷ Kelvin, threading through filaments over tens of millions of light-years. This warm-hot intergalactic medium contains between 30% and 50% of the universe's baryonic matter, providing a crucial clue in resolving the missing baryons problem. Weak gravitational lensing maps from the Dark Energy Survey confirm that these filaments are embedded within dark matter scaffolds, with filament densities reaching up to 10 times the cosmic mean at their cores, decreasing toward the surrounding voids. Simulations of cosmic evolution, such as Illustris TNG, Eagle, and the Millennium simulation, indicate that the cosmic web's pattern likely continues beyond the observable universe. Supervoids beyond our horizon could span 1–2 billion light-years, while clusters and filaments of comparable scale may exist, shaping unseen gravitational potentials. Predictions suggest that the influence of these structures could extend subtly into observable space, affecting galaxy motions, cosmic microwave background fluctuations, and the large-scale distribution of matter. Superclusters in the unobservable universe might reach masses greater than 10-18 solar masses, forming nodes in a vast cosmic network whose influence could extend into observable space. The dynamics within the cosmic web are intricate. Filamentary flows carry gas at velocities of several hundred kilometers per second toward cluster cores, where galaxy mergers and interactions trigger star formation and active galactic nuclei activity. In contrast, void interiors experience outward flows driven by dark energy, with expansion rates exceeding the average Hubble constant locally by up to 20%. Observations of galaxy peculiar velocities near void boundaries confirm this effect, revealing that void expansion plays a measurable role in shaping local large-scale motions. Even in the emptiest cosmic regions, faint dwarf galaxies, gas clouds, and dark matter halos trace the contours of space-time. Surveys using the Hubble Space Telescope, Sloan Digital Sky Survey, and the Dark Energy Spectroscopic Instrument have catalogued tens of thousands of galaxies in low-density regions, demonstrating that no void is truly empty. The interplay between these sparse objects and surrounding filaments provides critical information about the formation of galaxies in isolation, the distribution of dark matter, and the influence of dark energy on cosmic expansion. Black holes and extreme gravity. Black holes represent the most extreme manifestations of gravity in the universe, regions where the curvature of space-time becomes so intense that nothing, not even light, can escape. They form when massive stars exhaust their nuclear fuel and collapse under their own gravity. This collapse compresses the core into a singularity, surrounded by an event horizon, the boundary beyond which escape is impossible. Stellar mass black holes typically range from 5 to 100 solar masses, while supermassive black holes, found at the centers of galaxies, can reach billions of solar masses. For instance, Sagittarius A star, the Milky Way's central black hole, has a mass of roughly 4.1 million solar masses. Its gravitational influence governs the orbits of nearby stars, including S2, which moves at 7,650 kilometers per second and approaches within just 17 light-hours of the black hole. These measurements, made using adaptive optics on the Very Large Telescope in Chile, provide direct evidence of extreme gravity and offer a laboratory for testing general relativity. Supermassive black holes power some of the universe's brightest objects, quasars. When surrounding gas and dust fall toward the event horizon, they form an accretion disk, heating to millions of Kelvin and emitting X-rays and gamma rays. TON 618, one of the most massive quasars known, harbors a black hole of approximately 66 billion solar masses. Its luminosity exceeds 1040 watts, making it observable across 10 billion light-years. These luminous objects illuminate the intergalactic medium, providing indirect information about matter distribution in regions far beyond the reach of conventional telescopes. Intermediate mass black holes, with masses ranging from hundreds to hundreds of thousands of solar masses, provide clues about how supermassive black holes grow. Evidence of such black holes exists in dense star clusters, such as 47 Tucanae, where stellar dynamics suggest a central black hole of about 2,200 solar masses. Simulations indicate that these intermediate black holes could merge over time to form supermassive black holes, potentially occurring at redshifts of 1015, when the universe was less than 500 million years old. Black holes also produce relativistic jets, narrow streams of plasma accelerated to near light speeds. M87*, located 53 million light-years away, emits a jet extending 5,000 light-years. Matter in these jets reaches velocities exceeding 99.5% of the speed of light, indicated by Lorentz factors above 10. These jets regulate galaxy formation by heating surrounding gas and suppressing star formation in nearby regions, influencing large-scale cosmic structure. Observations of M87***'s shadow by the Event Horizon Telescope in 2019 confirmed the presence of a supermassive black hole with an event horizon roughly 38 billion kilometers across. Gravitational waves offer another window into black holes. Detected by LIGO and Virgo, these ripples in space-time originate from mergers of black holes ranging from 10 to over 150 solar masses. The event GW190521, detected in 2019, involved the merger of black holes of 85 and 66 solar masses, producing a single black hole of 142 solar masses and releasing energy equivalent to 8 solar masses in gravitational waves within a fraction of a second. These measurements allow scientists to study extreme gravitational environments at distances of billions of light-years, far beyond what electromagnetic observations can probe. Tidal disruption events occur when stars venture too close to a black hole. ASASSN 14 Li, located 290 million light-years away, revealed X-ray and ultraviolet emissions as a star was torn apart by a black hole of roughly 1 million solar masses. Studying these events provides insight into accretion physics, relativistic tidal forces, and the behavior of matter under extreme gravitational stress. Black holes also exist in clusters and groups, where their combined gravitational influence affects galaxy evolution. Ultraluminous X-ray sources in galaxies like NGC 1313 indicate populations of tens to hundreds of black holes within dense environments. In dwarf galaxies such as RGG 118, the presence of a 50,000 solar mass black hole shows that even low-mass galaxies can host these extreme objects, contributing to a continuous spectrum of black hole masses across the universe. Time dilation near black holes illustrates another extreme effect of gravity. A clock near the event horizon of a stellar mass black hole ticks millions of times slower than one far away. This warping of space-time can leave detectable imprints on gravitational waves or high-energy emissions. Accretion disks in these systems have orbital velocities approaching 0, 3c, temperatures exceeding 10 million Kelvin, and magnetic fields up to 100 million Gauss, demonstrating the intensity of physics under extreme gravity. Multi-messenger astronomy combines gravitational waves, electromagnetic radiation, and neutrino observations to reconstruct black hole activity. IceCube detected a 290 TeV neutrino from Blazar TXS 0506 plus 056, located 4 billion light-years away, coinciding with gamma-ray flares. Such events confirm that black holes accelerate particles to PV energies, turning them into natural cosmic laboratories for high-energy physics. Coordinated observations also allow scientists to map environments surrounding supermassive black holes and infer conditions in distant regions. In the vicinity of supermassive black holes, stars and gas clouds follow highly eccentric orbits, sometimes swinging perilously close to the event horizon. These near collisions generate tidal forces so extreme that they stretch and compress matter, creating luminous flares detectable across millions of light-years. High-resolution spectroscopy reveals shifts in emission lines caused by gravitational redshift and relativistic Doppler effects, providing direct measurements of space-time curvature. Magnetized plasma swirling around the black hole can form helical structures within jets. accelerating particles to energies exceeding those achievable in human-made accelerators. Around black holes, matter and energy interact in ways that push the limits of known physics. Accretion disks can reach millions of Kelvin, emitting intense X-rays while magnetic fields twist. Gravitational waves. Listening to the universe. Gravitational waves are ripples in the fabric of space-time, traveling at the speed of light, produced by some of the universe's most violent and energetic events. Predicted by Albert Einstein in 1916, through the general theory of relativity, these waves are distortions caused by the acceleration of massive objects, particularly those in asymmetric motion. For decades, gravitational waves remained theoretical because their effect on space-time is minuscule, altering distances by fractions smaller than the diameter of a proton across kilometers. It was not until the 14th of September 2015 that the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected the first direct signal, designated GW150914, from a merger of two black holes located approximately 1.3 billion light-years away. This observation confirmed Einstein's century-old prediction and opened a completely new way of observing the cosmos. The sources of gravitational waves are diverse, but the most commonly observed originate from the merger of compact objects, black holes, neutron stars, and combinations thereof. Stellar mass black hole mergers detected by LIGO and Virgo range from tens to hundreds of solar masses, with GW190521 involving black holes of 85 and 66 solar masses, forming a remnant of 142 solar masses and emitting energy equivalent to 8 solar masses in gravitational waves within less than a second. Such events release more energy than all the stars in the observable universe produce in that same period, but concentrated in the subtle distortion of space-time rather than light. Neutron-star mergers, though less massive than black hole binaries, produce signals that reveal entirely different physics. The event GW170817, detected in 2017, occurred 130 million light-years away and involved two neutron stars of approximately 1.36 and 1.6 solar masses. This merger generated a kilonova, visible across multiple wavelengths, and was accompanied by gamma-ray bursts detected by Fermi and integral satellites. Neutron-star mergers are key to understanding the synthesis of heavy elements. Observations of GW170817 confirmed that elements such as gold, platinum, and uranium originate in these extreme collisions, linking gravitational wave astronomy directly to chemical evolution across the universe. Gravitational wave signals carry information not only about mass and energy, but also about the spin, orientation, and eccentricity of the merging objects. Black hole mergers, especially those with significant spin alignment or misalignment, produce characteristic chirps, where frequency and amplitude rise rapidly as the objects spiral inward. The waveforms detected by LIGO and Virgo allow astrophysicists to reconstruct the dynamics of these mergers with extraordinary precision. As of 2025, more than 100 gravitational wave events have been catalogued, ranging in distance from 100 million to over 10 billion light-years, offering a glimpse into the activity of the universe that is far beyond what light-based telescopes can reveal. Future gravitational wave observatories, such as the Laser Interferometer Space Antenna LISA, scheduled for launch in the 2030s, will expand sensitivity to much lower frequencies. LISA will detect supermassive black hole mergers with masses up to 1 billion solar masses, allowing the study of galactic evolution in distant regions. Gravitational waves also provide an unprecedented tool for probing regions of the universe that are otherwise obscured. Electromagnetic waves cannot escape from regions shrouded in dense gas, such as the cores of merging galaxies or the environments surrounding supermassive black holes. In contrast, gravitational waves pass unimpeded, allowing scientists to listen to the dynamics of these hidden zones. The frequency, amplitude, and polarization of these waves encode the distribution of mass and energy, revealing the mass ratios of colliding objects, orbital eccentricities, and even the presence of additional bodies in triple systems. Observations of gravitational waves have revealed unexpected phenomena. Intermediate mass black holes, bridging the gap between stellar mass and supermassive black holes, were long hypothesized but lacked direct detection. GW 190521 provided the first strong evidence, confirming a remnant mass of 142 solar masses. This discovery challenges existing models of black hole formation and provides evidence of intermediate mass black holes that were previously hypothesized but undetected. Neutron stars themselves provide extreme laboratories for physics. These remnants have densities exceeding 10-17 kilograms per cubic meter, surpassing nuclear densities. When they collide, they produce gravitational waves that encode information about the equation of state of ultra-dense matter. By measuring the tidal deformation during inspiral, scientists can infer whether a neutron star's core contains exotic states of matter, such as quark-gluon plasma or hyperons. GW 170817 allowed the first constraints on neutron star radii, suggesting values between 11.9 and 13.6 kilometers, despite their mass exceeding that of the Sunday. Such measurements extend our understanding of fundamental physics to scales inaccessible on Earth. Gravitational waves propagate through the universe largely unaffected by intervening matter or radiation. This property enables detection of events at redshifts well beyond the capabilities of electromagnetic observation. For instance, mergers at redshift Z to 10, corresponding to 13.2 billion years ago, may be detectable with future observatories. These signals could reveal the formation of the first black holes, the assembly of early galaxies, and even the dynamics of primordial star clusters that lie beyond the current observable universe. Multi-messenger observations enhance the educational power of gravitational waves. The combination of light, neutrinos, and gravitational waves allows reconstruction of extreme cosmic events. For example, high-energy neutrinos detected by IceCube in 2018, coinciding with Blazar TXS 0506 plus 0564 billion light-years away, suggest particle acceleration near supermassive black holes. Gravitational waves from these environments provide complementary information about mass distribution and orbital dynamics, offering a more complete picture of high-energy processes shaping the cosmos. The early universe, traces of primordial times. In the earliest fractions of a second after the Big Bang, the universe consisted of a dense, hot plasma with temperatures exceeding 10 billion Kelvin, composed mainly of quarks, gluons, electrons, neutrinos, and photons. Quarks combined to form protons and neutrons during baryogenesis, creating the building blocks for atomic nuclei. Traces of these early conditions remain observable today in the distribution of matter, the temperature of the cosmic microwave background, and the relative abundances of light elements. Between approximately 3 minutes and 20 minutes after the Big Bang, nucleosynthesis occurred. In this brief window, light elements such as hydrogen, helium, and traces of lithium and beryllium were formed. Observations show that about 75% of baryonic matter today is hydrogen, and roughly 25% is helium-4 by mass, consistent with predictions from the Big Bang nucleosynthesis models. Deuterium, a heavy isotope of hydrogen, constitutes roughly 0.02% of baryonic matter, and its observed abundance in distant gas clouds matches theoretical expectations within a margin of 1–2%, providing a precise probe of early universe conditions. Lithium-7, although rarer at 1 part in 10 billion, offers an additional test of nuclear processes during the primordial era, although its observed abundance presents a small but persistent discrepancy with theory, known as the cosmological lithium problem. By roughly 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, a process called recombination. This allowed photons to travel freely for the first time, creating what we now detect as the cosmic microwave background, CMB. The CMB has an average temperature of 2.725 K and exhibits minute temperature fluctuations of 1 part in 100,000. These anisotropies, first mapped with precision by the Wilkinson Microwave Anisotropy Probe, WMAP, and later with Planck, reveal density variations that would later seed galaxies and clusters. Planck's 2018 data indicate that the largest fluctuations correspond to regions roughly 500 million light-years across today, and that the universe is composed of approximately 68% dark energy, 27% dark matter, and 5% ordinary matter ratios that remain critical for modeling both observable and unobservable regions. The polarization of the CMB adds another layer of insight. E-mode polarization patterns correspond to density fluctuations, while B-mode patterns could indicate the presence of primordial gravitational waves, ripples in space-time generated during inflation. Detecting B-mode polarization at scales corresponding to multipoles L to 100–200 could provide evidence for inflationary expansion, a process in which the universe doubled in size at least 26 times in a fraction of a second. Experiments such as BICEP-2 and the South Pole Telescope continue to refine upper limits on the tensor-to-scalar ratio, R, which quantifies the strength of these primordial gravitational waves, with the current upper limit set at R is less than 0.036. Inflation also produced quantum fluctuations in energy density that were stretched across cosmic scales. These fluctuations became the seeds for the cosmic web observed today. Measurements of large-scale structure, such as those from the Sloan Digital Sky Survey and the Dark Energy Survey, show filamentary networks of galaxies separated by cosmic voids tens to hundreds of millions of light-years wide. By modeling the distribution of matter as a function of redshift, cosmologists can infer the spectrum of primordial density fluctuations and the physical mechanisms that govern the universe beyond the visible horizon. These studies indicate that fluctuations follow a nearly scale-invariant spectrum with a slight tilt, characterized by a spectral index of n. S is approximately equal to 0.965, consistent with predictions from single-field slow-roll inflation models. The chemistry of the early universe also left detectable fingerprints. Light element ratios, combined with measurements of the CMB baryon-to-photon ratio, ITER is approximately equal to 6 × 10⁻10, provide a precise accounting of the universe's content in its first minutes. Observations of deuterium in high redshift quasar absorption systems yield values of D, H, is approximately equal to 2.53 × 10⁻5, matching theoretical expectations with remarkable precision. These measurements not only confirm the hot Big Bang model, but also constrain the number of relativistic species in the early universe, currently estimated at n. F is approximately equal to 2, 99 plus or minus 0.17, consistent with 3 active neutrino flavors. The formation of the first stars, or population 3 stars, occurred between 100 and 250 million years after the Big Bang. These stars, with masses likely ranging from 30 to 300 solar masses, were composed almost entirely of hydrogen and helium. Their short lifespans, typically a few million years, produced the first supernovae, which seeded the interstellar medium with heavier elements like carbon, oxygen, and iron, enabling the later formation of population 2 and population Ver stars. Observations from JWST have recently detected galaxies at redshifts Z to 1314, corresponding to 300 and 350 million years after the Big Bang, providing the first direct view of star formation in the universe's primordial epoch. High redshift quasars, powered by supermassive black holes, also trace the early universe. The quasar J 313-1806, discovered at Z equals 7.64, existed just 670 million years after the Big Bang and hosts a black hole of 1.6 billion solar masses. Its rapid growth challenges conventional models of black hole accretion, suggesting that extreme conditions in the early universe may have produced massive seeds through direct collapse or dense star cluster mergers. These extreme objects illuminate the surrounding intergalactic medium, producing Lyman alpha emission and ionizing photons that contribute to cosmic reionization between 400 million and 1 billion years after the Big Bang. Observations of the 21-centimeter hydrogen line offer additional insight into the primordial universe. The experiment to detect the global epoch of reionization signature, EDGES, reported a signal at a redshift of Z to 17, corresponding to roughly 180 million years after the Big Bang. This absorption feature implies that the first stars and black holes were already influencing the thermal state of neutral hydrogen, marking the transition from the cosmic dark ages to the epoch of luminous structures. Measurements of the 21 cm line across multiple redshifts provide constraints on star formation rates, the timing of reionization, and the influence of radiation fields beyond the observable horizon. Primordial magnetic fields, another relic of the early universe, may have been generated during inflation or phase transitions, such as the electroweak symmetry breaking at temperatures near 100 GeV. Observational constraints from the Planck satellite place. The comoving field strength at B is less than 1 ng on megaparsec scales, suggesting that even weak fields in the early universe could seed galactic magnetism observed in galaxies today with microgauss level strengths. Cosmic microwave background anisotropies, Faraday rotation measurements, and high redshift galaxy observations all help trace these primordial influences across billions of years. Neutrinos decoupled from the primordial plasma roughly 1 second after the Big Bang, creating a cosmic neutrino background with a temperature of 1.95 K today. While these relic neutrinos are extremely difficult to detect directly, their existence affects the expansion rate and the formation of large-scale structures. The effective number of neutrino species, measured through CMB observations, influences the sound horizon at recombination, which in turn affects the angular scale of acoustic peaks detected by Planck. Such measurements provide an indirect window into particle physics at energies unattainable in terrestrial laboratories. Dark matter and dark energy. The stars and galaxies that paint the night sky represent only a small fraction of the universe's true content. Beneath this glowing architecture lies an invisible framework, an unseen scaffolding that holds everything together. This is dark matter, a mysterious form of matter that neither emits nor absorbs light, yet exerts a powerful gravitational influence on all cosmic structures. Although it cannot be seen, its presence is inferred from its effects, from the motions of galaxies to the bending of light across billions of light years. Dark matter accounts for roughly 26.8% of the universe's total mass-energy budget, compared to only 4.9% for ordinary or baryonic matter. The rest, about 68.3%, is dark energy, the force driving cosmic acceleration. To understand the universe's outermost regions and ultimate boundaries, one must first grasp the invisible power shaping it from within. The story of dark matter began in the early 20th century with the Swiss astronomer Fritz Zwicky, who in 1933 studied the Coma Cluster, a collection of more than 1,000 galaxies located 320 million light-years away. Zwicky measured the galaxies' velocities and found that they were moving far too quickly to be gravitationally bound by their visible mass alone. He proposed the existence of unseen Dunkel materia, dark matter, to account for the missing mass. His idea, largely dismissed at the time, would later become one of the cornerstones of modern cosmology. 4 decades later, American astronomer Vera Rubin and her collaborator Kent Ford observed spiral galaxies such as Andromeda, M31, and NGC 3198, using advanced spectrographs at Kitt Peak National Observatory. To their surprise, they discovered that stars far from galactic centers orbited at nearly the same velocity as those near the core. According to Newtonian physics, orbital speeds should decrease with distance. Instead, they remain flat. This discrepancy revealed that galaxies are embedded in vast halos of unseen mass, evidence that dark matter surrounds and stabilizes galaxies, influencing their dynamics across every scale. Today, cosmologists understand that dark matter forms the backbone of the cosmic web, the immense network of filaments and voids spanning the universe. Simulations such as the Millennium Simulation 2005 and Illustris TNG 2018 reveal how dark matter clumps under gravity, forming dense nodes where galaxies gather, connected by filaments stretching hundreds of millions of light-years. Ordinary matter follows this hidden structure, condensing within the gravitational wells of dark matter to form stars, galaxies, and clusters. The visible universe, the part we can see, merely traces the luminous edges of this invisible cosmic skeleton. Evidence for dark matter extends across multiple scales. In the Bullet Cluster 1E0657-56, located about 3.7 billion light-years away, 2 galaxy clusters collided at tremendous speeds. Observations from the Chandra X-ray Observatory and the Hubble Space Telescope revealed a striking separation between hot gas, which represents normal matter, and the overall gravitational mass. Mapped by gravitational lensing, the majority of mass had passed through unaffected, showing that dark matter interacts primarily through gravity, not electromagnetism. Later observations of systems like Max J25, 4 to 1222, confirmed this pattern, strengthening the case that dark matter is a distinct, collision-less component of the cosmos. Dark matter's influence reaches even to the edges of the observable universe. Beyond the light of galaxies, its gravitational effects continue to sculpt space. The outermost structures visible to our telescopes, galaxy clusters at redshifts beyond Z = 7, lie within massive dark matter halos, each extending millions of light-years across. As we approach the particle horizon, roughly 46.5 billion light-years away, the patterns of galaxy distribution still reflect the hidden web beneath. Computer models suggest that this dark network extends smoothly into regions far beyond our horizon, shaping the unobservable cosmos in similar ways. The interplay between dark matter and dark energy defines the universe's fate at its limits. While dark energy drives galaxies apart through accelerated expansion, dark matter exerts an opposing gravitational force that binds galaxies and clusters together. On small scales, dark matter resists expansion, holding galaxies intact. On the largest scales, dark energy dominates, pushing regions of the cosmos beyond our reach. Over the next 100 billion years, galaxies outside the local group will drift past our event horizon, their light redshifted into invisibility. Yet within this cosmic isolation, dark matter will continue to stabilize local structures, even as the universe's edges recede faster than light due to the stretching of space itself. Despite its dominant role, dark matter has never been directly detected. Physicists have built increasingly sensitive experiments to find it. Lux Zeppelin, LZ, located in South Dakota's Sanford Underground Research Facility, seeks WIMP's weakly interacting massive particles using 10 tons of ultra-pure liquid xenon. In Italy's Gran Sasso laboratory, the Xeno NNT detector searches for faint flashes of light that could indicate WIMP collisions. Other projects, such as Super CDMS in Canada and Panda X4 tons in China, aim for even greater sensitivity. So far, all have reported null results, constraining the WIMP nucleon cross-section below 10 to the power of negative 48 cm squared. Alternative candidates like axions, proposed by Frank Wilczek and Roberto Pecce, or sterile neutrinos, remain viable possibilities. Each discovery or non-detection refines our picture of what dark matter might be or what it is not. Indirect evidence continues to mount. Observations from the Planck satellite, combined with baryon acoustic oscillation data and Type Ia supernova measurements, show that the universe's structure could not exist without dark matter. Galaxies formed far earlier than visible matter alone would allow. In numerical simulations, removing dark matter erases the filamentary structure of the cosmos entirely. Galaxies fail to form in time, and the universe remains diffuse and unstructured. At the outermost edges, dark matter may extend far beyond the observable horizon, binding vast superclusters that we will never see. Some cosmologists speculate that variations in dark matter density could exist in these unseen regions, influencing the large-scale curvature of the cosmos. Others propose that dark matter particles could decay over cosmic timescales, subtly altering the distribution of mass energy as the universe evolves. If these variations exist beyond our horizon, their gravitational imprints might still affect the motion of nearby galaxies, contributing to the so-called dark flow, a puzzling large-scale motion of galaxy clusters, first reported by Alexander Kishlinsky and colleagues in 2008 and still debated in recent analysis. Dark matter also serves as a bridge between the observable and the unknown. Through gravitational lensing, where massive structures bend light from distant galaxies, scientists map the invisible mass distribution across billions of light-years. Upcoming missions, such as Euclid, launched in 2023, and NASA's Nancy Grace Roman Space Telescope, planned in 2027, will refine these maps with unprecedented accuracy, tracing the hidden architecture of space-time all the way to the cosmic edge. Multiverse theories and beyond. One of the most provocative and potentially transformative ideas in modern cosmology is the notion of a multiverse, a collection of universes, each with its own physical laws, constants, and histories. While the concept stretches the imagination, it arises naturally from multiple branches of contemporary physics, including cosmic inflation, string theory, and quantum mechanics, providing theoretical approaches to describe regions beyond the observable universe. In the framework of eternal inflation, the universe does not expand uniformly everywhere. First proposed by physicists André Linde, Paul Steinhardt, and Alex Vilenkin in the 1980 seconds. Eternal inflation suggests that while some regions stop inflating and form pocket universes, other regions continue inflating indefinitely. Our observable universe, about 92 billion light-years in diameter when accounting for expansion, is just one of these pockets. Outside this observable bubble, inflationary space expands faster than light, creating boundaries that prevent any information from reaching us. These pockets could exhibit different matter densities, variations in the strength of fundamental forces, or alternative particle content. Certain models predict universes with particle physics, distinct from the standard model, or different cosmological histories, where structures such as stars or galaxies do not form. String theory, one of the leading candidates for a unified theory of everything, provides a complementary lens on the multiverse. The theory posits up to 10 or 11 spatial dimensions, most of which are compactified or hidden at scales below 10 to the power of -30 meters. Different ways of compactifying these extra dimensions generate universes with unique physical constants, particle masses, and fundamental interactions. This leads to a landscape of possible universes, each arising from distinct configurations of these hidden dimensions. Estimates suggest that there could be as many as 10 to the power of 500 distinct vacua within the string theory landscape, a number so vast that even the observable universe is a negligible subset. While most of these universes lie entirely beyond the observable horizon, their statistical distribution allows theoretical predictions for the range of physical constants that might occur. Quantum mechanics offers yet another perspective on the multiverse. The many worlds interpretation, formalized by Hugh Everett in 1957, proposes that every quantum event spawns separate branches of reality, creating a constantly branching tree of parallel universes. According to this interpretation, every possible outcome of a quantum measurement is realized somewhere. In this framework, regions beyond our observation correspond to different branches in which quantum events have taken alternative outcomes. For example, the behavior of an electron in a distant atom could differ across branches, producing universes with varied histories of quantum events. Although experimental verification is currently not feasible, the interpretation is mathematically consistent and provides a way to describe unobservable quantum outcomes. Multiverse theories also help contextualize the long-standing fine-tuning problem. Physical constants, such as the cosmological constant, L10 to the power of -122 in Planck units, the mass of the electron, 9.11 times 10 to the power of -31 kilograms, or the strength of the strong nuclear force, appear precisely calibrated to allow the formation of stable atoms, stars, and galaxies. In a single universe scenario, this degree of fine-tuning is puzzling. The odds of these constants falling within life-permitting ranges seem astronomically low. In a multiverse containing potentially 10 to the power of 500 universes with randomly distributed parameters, life-permitting conditions could occur in some subset. This provides a statistical framework in which our universe's properties are consistent with the existence of observers, without implying intentional design. Some multiverse models also suggest potential observational signatures, albeit indirect. For instance, collisions between neighboring universes could leave imprints on the cosmic microwave background. In 2007, researchers at the University of Cambridge and the Perimeter Institute proposed that circular anomalies or temperature asymmetries in the CMB could be evidence of past bubble collisions. While analyses of Planck and WMAP data have yet to provide conclusive evidence, these studies demonstrate that multiverse hypotheses, although largely speculative, remain within the scope of empirical investigation. Similarly, large-scale anisotropies, such as the CMB cold spot discussed in Chapter 12, could be analysed for possible gravitational effects from other bubble universes. Mathematically, eternal inflation implies that the number of universes could be infinite. If the inflationary process continues without bound, new bubble universes are constantly nucleating, each with unique physical conditions. Some of these universes may collapse quickly, forming black hole-like singularities, while others expand indefinitely, producing vast cosmic regions beyond our horizon. Models by Andre Linde and Alan Guth suggest that this process could generate regions larger than 10 to the power of 100 times the volume of our observable universe, with energy densities ranging from near zero to the Planck scale, 10 to the power of 19 GeV. According to these models, such regions would be causally disconnected, consistent with the theoretical predictions of inflationary physics. The multiverse framework also intersects with anthropic reasoning in more complex ways. Beyond explaining fine-tuning, it provides potential resolutions to the hierarchy problem in particle physics, including the relative weakness of gravity compared to other forces and the smallness of the cosmological constant. By modelling a statistical distribution of universes with varying constants, physicists such as Leonard Susskind and Raphael Bousso have argued that our universe's seemingly improbable values may be typical among life-permitting universes, even if extraordinarily rare in absolute terms. This approach shows how the concept of unobservable universes can inform theoretical models in physics and cosmology. Multiverse theories extend current understanding of cosmic boundaries. The edge of the observable universe may not mark a physical limit, but rather a transition to a broader ensemble of universes with distinct histories and laws. Some universes could be relatively similar to ours, differing only in minor constants, while others could be radically different, with no atoms, stars, or familiar chemistry. These realms are inaccessible to light, gravitational waves, or any conventional observational technique, though they are consistent with theoretical models based on fundamental physics. By integrating insights from inflationary cosmology, string theory, and cosmic horizons and event limits, cosmic horizons define the ultimate limits of what can be observed. The observable universe extends roughly 46.5 billion light-years in every direction, determined not by the age of the universe alone, but by the expansion of space itself. Light from more distant regions has not had time to reach us, and due to cosmic expansion, some regions are already receding faster than the speed of light, creating a hard, observational limit. This boundary is known as the particle horizon, a radius calculated from the integral of the speed of light over the universe's expansion history, yielding a comoving distance of approximately 46.5 billion light-years. Beyond this horizon lies matter that may exist, but which will never be detectable through conventional electromagnetic signals. Closely related to the particle horizon is the concept of the event horizon of the universe, which describes the furthest distance from which light emitted now can ever reach us in the future. Due to the accelerated expansion driven by dark energy, modelled as a cosmological constant, L is approximately equal to 1.1 times 10 to the power of negative 52 meters. Negative 2, regions currently observed at redshifts Z is greater than 1.7, are already beyond our cosmic event horizon. Galaxies such as GNZ11 at a redshift of Z equals 11.09 are observed as they were just 400 million years after the Big Bang, yet their future light may never reach distant civilizations as the universe continues to expand exponentially. The particle horizon shows the limits of our past observations, while the event horizon indicates the regions whose future light will remain inaccessible. The Hubble radius, approximately 14.4 billion parsecs, represents another operational limit tied to expansion rate, h. 0 is approximately equal to 67.4 kms, mpc, as measured by Planck 2018. Objects beyond this radius recede faster than light relative to us, not violating relativity, but demonstrating that cosmic expansion operates independently of local spacetime. This expansion creates a cosmic light-speed barrier on ultra-large scales, meaning that even photons traveling at 3 × 10 to the power of 8 meters per second cannot overcome the space stretching between galaxies at sufficient distances. Observations of type Ia supernovae across redshifts Z equals 0.0, 1, 2.3 provide direct evidence for this accelerated expansion, indicating the scale at which structures become causally disconnected. Gravitational horizons also emerge when considering mass distributions on cosmic scales. Superclusters such as Laniakea, spanning 520 million light-years and containing over 100,000 galaxies, define local gravitational domains. Beyond such structures, expansion dominates over local attraction. Within these regions, peculiar velocities, motions induced by local gravity, can reach hundreds of kilometers per second, as mapped using the Cosmic Flows 3 survey, revealing flows of matter toward the Great Attractor, located roughly 150 million light-years away. These gravitationally bound regions demonstrate how local gravity can counteract cosmic expansion, keeping some structures interconnected while more distant matter continues to recede. Cosmic horizons are not only defined spatially but also temporally. The light we detect from distant galaxies represents snapshots in time. For instance, the galaxy cluster Max-J 1149, 5 + 2223 at Z is approximately equal to 0.544. Emits light that took nearly 5.4 billion years to reach Earth, while the photons we observe from the CMB left the universe approximately 380,000 years after the Big Bang, spanning a comoving distance of 46 billion light-years. Temporal horizons limit observations. Even with perfect detectors, events beyond certain distances remain frozen in the past, inaccessible in real time. Instruments like JWST and ALMA extend our reach into these early epochs, but they remain confined by the horizon set by cosmic expansion. Inflation in the universe's first 10, -32 seconds profoundly shaped the size of observable regions. Quantum fluctuations during this exponential expansion were stretched to scales now, measuring hundreds of millions of light-years, imprinting the anisotropies seen in the CMB. These fluctuations define the correlation length for structures across the observable universe, setting the scale at which cosmic variance limits our statistical certainty about regions beyond our sight. The largest overdense regions, identified in surveys such as the Sloan Digital Sky Survey, spanning superclusters of 200–400 million light-years, align with these primordial patterns, while vast cosmic voids, some exceeding 300 million light-years across, trace the underdense counterparts. The overall cosmic web reflects both local gravitational interactions and the imprint of inflationary expansion. High redshift gamma-ray bursts, GRBs, provide additional insight into the limits of observability. GRB 090423, detected at Z, is approximately equal to 8.2 emitted photons over 13 billion years ago. Such extreme events allow astronomers to probe the intergalactic medium's ionization state in the early universe and constrain matter distributions approaching the particle horizon. Neutrino observatories like IceCube also contribute, detecting high-energy neutrinos potentially originating from active galactic nuclei at Z is greater than 2. These neutrinos interact weakly and can traverse regions that photons cannot, providing information about regions near the ultimate observational limits. Gravitational waves extend the horizon concept further. Signals from binary black hole mergers, such as GW150914, detected by LIGO in 2015, originated approximately 1.3 billion light-years away, while neutron star mergers like GW170817 came from roughly 130 million light-years. Future observatories like LISA, with sensitivity to millihertz frequencies, aim to detect supermassive black hole mergers at redshifts Z is greater than 10, potentially providing information about structures forming within the first 500 million years after the Big Bang, near the observational limits set by the particle horizon. These multi-messenger signals provide information about regions that photons cannot reach. The concept of horizons also has implications for dark energy and the universe's expansion. Observations of baryon acoustic oscillations, BAO, at redshifts Z is approximately equal to 0.12.5. Map the expansion history and indicate that dark energy dominates the cosmic energy budget today. If dark energy remains a cosmological constant, regions currently at Z is greater than 1.7 will recede beyond causal contact within tens of billions of years. Simulations of long-term expansion, such as the Millennium and Illustrious TNG projects, show that structures will eventually become gravitationally isolated as expansion continues. High-energy phenomena at the edge of space. At the furthest reaches of the observable universe, quasars, gamma-ray bursts, cosmic rays, black hole jets, colliding galaxy clusters, and tidal disruption events occur at extreme energies. These phenomena can be observed across billions of light-years, providing measurable signals from distant regions. Quasars, or quasi-stellar objects, are powered by supermassive black holes weighing from 1 million to over 10 billion times the mass of the Sunday. Euler's J 1342 plus 0928 at a redshift of 7.54 is more than 13 billion light-years distant. Its black hole has an estimated mass of 800 million solar masses. Quasars can emit light up to 100 trillion times the sun's luminosity across the spectrum from X-rays to radio waves. Absorption lines in quasar spectra allow astronomers to measure the hydrogen content between galaxies. Some quasar jets extend over 100 kiloparsecs. Gamma-ray bursts, GRBs, release in seconds an amount of energy comparable to the Sun's total 10 billion-year output. GRB 090423 at redshift 8.2 occurred about 630 million years after the Big Bang. Long-duration GRBs result from the collapse of massive stars, while short-duration bursts originate from neutron star collisions. Instruments such as SWIFT, Fermi, and Integral detect these events and their afterglows in X-ray, optical, and radio wavelengths. These observations provide information about chemical abundances and magnetic fields in the early intergalactic medium. High-energy cosmic rays, protons, and atomic nuclei accelerated to near-light speed are observed at Earth through extensive air showers recorded by the Pierre Auger Observatory and high-energy neutrinos detected by ICE. Cube. Some cosmic rays reach energies above 10-20 electron volts, about 100 million times higher than particles accelerated in the Large Hadron Collider. Possible sources include active galactic nuclei, supernova remnants, and colliding galaxy clusters. Cosmic rays interact with intergalactic magnetic fields over megaparsec scales. Supermassive black holes are sources of extreme energy, with jets observed by Chandra X-ray Observatory and the Very Large Array moving at over 99% of the speed of light, and with kinetic energy outputs of 10, 46, 10, 47 erg/s. These jets interact with interstellar gas, compressing and heating material in their paths. Gravitational waves from black hole mergers detected by LIGO and Virgo provide measurements of space-time distortions caused by massive objects at cosmological distances. Binary supermassive black hole mergers, as predicted by hierarchical galaxy formation models, may generate gravitational waves detectable by future space-based observatories such as LISA, offering direct observational evidence of these high-energy events. Colliding galaxy clusters generate shocks that heat intergalactic gas to tens of millions of Kelvin. Subclusters producing turbulence, X-rays, and extended magnetic fields. Observations of these cluster collisions reveal the dynamics of dark matter and baryonic matter on megaparsec scales, providing data for modeling the evolution of large-scale cosmic structures. Tidal disruption events occur when a star passes within the tidal radius of a supermassive black hole and is torn apart. eROSITA has detected over 1,000 such events, with peak luminosities up to 1045 erg/s. Some events generate relativistic jets observable in radio wavelengths across tens of megaparsecs. Optical and ultraviolet flares from these disruptions provide detailed measurements of accretion processes and the structure of black hole accretion disks. Magnetic fields in high-energy environments exhibit coherent structures. In galaxy clusters, field strengths reach micro-Gauss levels, while relativistic jets contain magnetic fields tens of times stronger. Polarized radio emissions show coherence over megaparsec scales. Measurements from the Carl G. Jansky Very Large Array and LOFAR indicate magnetic coherence lengths exceeding 100 kiloparsecs in cluster outskirts. These observations provide data for understanding particle trajectories and the dynamics of intra-cluster gas in magnetized environments. Fast radio bursts, FRBs, are millisecond duration pulses of coherent radio emission, with some observed at redshifts greater than 1. Over 1,000 FRBs have been catalogued, including repeating bursts associated with magnetars, neutron star mergers, or active galactic nuclei. The dispersion measures of FRBs provide direct estimates of electron densities in the intergalactic medium. Analysis of FRB arrival times and polarization also allows measurement of magnetic fields, turbulence, and the distribution of baryons over cosmological distances, offering quantitative constraints on the properties of diffuse intergalactic space. Intermediate mass black holes, with masses between 10.3 and 10.5 solar masses, have been detected in nearby dwarf galaxies and globular clusters. Observed X-ray luminosities of 10, 4010, 42 erg/s indicate active accretion, providing direct evidence for their presence and influence on surrounding gas. The detection of these objects helps refine models of black hole formation and early growth, indicating that similar black holes could exist in regions beyond current observational capabilities and may contribute to the evolution of local, stellar, and gas environments. Supernovae are major contributors to high-energy astrophysical processes. Core collapse supernovae expel matter at velocities exceeding 10,000 kilometers per second and release energies around 10.42 erg/s, distributing heavy elements such as iron, oxygen, and carbon into the interstellar and intergalactic medium. Type Ia supernovae, produced by white dwarf detonations, generate predictable light curves used as standard candles to measure cosmic distances. Observations of high redshift supernovae provide empirical constraints on the expansion history of the universe and models of dark energy, as well as on the formation and growth of large-scale cosmic structures. The future of cosmic exploration. As observational capabilities expand, regions beyond the current limits of the observable universe are becoming accessible to indirect study. The coming decades will see significant advancements in astronomy, astrophysics, and cosmology, enabled by improvements in telescope technology, multi-messenger detection, and computational simulations. These developments are expected to provide measurable information about previously hidden regions, offering empirical constraints on the formation and evolution of cosmic structures and the distribution of matter on the largest scales. Next-generation telescopes are set to revolutionize our view of the distant universe. The James Webb Space Telescope, JWST, has already captured galaxies at redshifts greater than 13, meaning their light originated when the universe was under 400 million years old. JWST's near-infrared camera, NIRC-CAM, and mid-infrared instrument, MIRI, have resolved star-forming regions with sizes less than 1,000 light-years, revealing the assembly of galactic structures in unprecedented detail. Following JWST, the Nancy Grace Roman Space Telescope, expected to launch in the mid-2020s, will survey areas exceeding 2,000 square degrees with a wide-field instrument that is 100 times more efficient than Hubble. Roman's mission includes identifying faint dwarf galaxies at the cosmic frontier, mapping dark matter via gravitational lensing, and indirectly constraining the distribution of matter in regions beyond direct observation. Ground-based observatories are also pushing the frontier. The extremely large telescope ELT in Chile, with its 39-meter primary mirror, will resolve individual stars in galaxies over 10 billion light-years away, while the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will catalogue tens of billions of galaxies over a decade, tracing large-scale structure evolution. Instruments like the Square Kilometre Array SKA, once operational, will detect neutral hydrogen emissions across redshifts of 0.1 to 20, effectively mapping the cosmic web in regions previously unreachable. These telescopes will help refine our understanding of galaxy formation, intergalactic gas flows, and the faint imprints of early cosmic expansion. Multi-messenger astronomy promises to reveal extreme events and hidden structures far beyond the observable universe. Gravitational wave observatories like LIGO, Virgo, CAGRA, and the planned Laser Interferometer Space Antenna, LISA, will detect mergers of black holes and neutron stars at distances exceeding 10 billion light-years. Each gravitational wave signal encodes the masses, spins, and orbital dynamics of colliding compact objects, providing indirect information about star formation, metallicity, and galaxy evolution in inaccessible regions. IceCube in Antarctica detects neutrinos above 100 TeV, while future experiments like KM3, NEET, and the Pacific Ocean Neutrino Experiment, P1, will increase detection sensitivity, enabling identification of cosmic accelerators billions of light-years away. Even in the absence of electromagnetic signals, gravitational waves and neutrinos provide measurable information about energetic processes, mass distributions, and nuclear synthesis, allowing scientists to infer properties of cosmic regions outside the direct line of sight. Advanced computational astrophysics is essential to extending our reach into the hidden universe. Large-scale cosmological simulations, including Illustris TNG, the Millennium Simulation, and EAGLE, model the formation and evolution of billions of galaxies across volumes exceeding 300 cubic megaparsecs. By incorporating baryonic physics, dark matter interactions, and cosmic expansion, these simulations predict galaxy clustering, filament formation, and void evolution far beyond the observable sphere. The next generation of exascale simulations aims to track over 1 trillion particles across volumes of more than 1 cubic gigaparsec, allowing scientists to study hypothetical structures in regions permanently beyond detection. These computational models also generate quantitative predictions for rare high-energy phenomena such as gamma-ray bursts, tidal disruption events, and supermassive black hole mergers, which can be directly compared with observational data to interpret signals from distant or indirectly observable regions. Emerging areas of fundamental physics may provide new methods to probe the universe beyond its observational limits. Primordial gravitational waves, generated during cosmic inflation, could leave subtle polarization patterns in the cosmic microwave background detectable by experiments such as CMBS-4 and LIGHTBIRD. The detection of such patterns would offer a direct window into physics at energies of 10 or 16 GeV, potentially revealing interactions in regions that remain forever unobservable in electromagnetic light. Quantum cosmology models, including loop quantum gravity and string theoretic approaches, suggest that the universe may harbor multiple causally disconnected regions, or pocket universes. Although direct empirical verification is difficult, statistical studies of large-scale structure and anomalies in the cosmic microwave background can yield measurable constraints on processes that may occur in regions currently inaccessible to direct observation. Observational and theoretical advances are complemented by experimental innovations in high-energy astronomy. Future X-ray observatories like Athena and Lynx will measure the hot intergalactic medium in clusters and filaments up to redshifts of 3, while next-generation gamma-ray detectors, such as the Cherenkov Telescope Array CTA, will detect TeV emission from blazars, active galactic nuclei, and supernova remnants billions of light-years away. By combining electromagnetic, gravitational, and particle observations, scientists can construct detailed models of the unseen universe, including dark matter halos, galaxy interactions, and energetic feedback processes shaping cosmic evolution. Even as exploration focuses on observation and simulation, interstellar and intergalactic travel remains a distant prospect. Technological proposals such as Breakthrough Starshot envision sending gram-scale probes to nearby stars at 20% of the speed of light. Yet practical exploration of regions beyond the observable universe lies beyond current capabilities. Nevertheless, theoretical and computational methods now allow researchers to quantify properties of regions that cannot yet be directly observed. By combining mathematical modeling, machine learning, and multi-messenger datasets, scientists can generate predictive maps of galaxy formation, star cluster distributions, and filamentary structures, providing testable hypotheses about the large-scale universe. The combination of precise observations, advanced simulations, and theoretical modeling is enhancing understanding of previously unobserved cosmic regions. Comparing observational data with simulation outputs allows the identification of anomalies such as missing satellite galaxies, atypical star formation rates, or unusual mass distributions, which can refine models of large-scale structure. This iterative approach provides a systematic framework for testing hypotheses about regions beyond current observational limits. In addition to cosmology and galaxy evolution, the study of extreme environments continues to illuminate distant regions. Multi-messenger detections of neutron star mergers reveal sites of rapid neutron capture, array process, nucleosynthesis, forming heavy elements like gold, platinum, and uranium. Observations of relativistic jets from quasars and microquasars, combined with simulations of magnetohydrodynamics, provide insights into particle acceleration and magnetic field amplification in regions billions of light-years away. Such data inform models of energetic feedback across the cosmos, including areas beyond direct observation. By the mid-21st century, the integration of next-generation observatories, high-resolution simulations, and multi-messenger datasets is expected to enable detailed mapping of galaxies, filaments, voids, and high-energy phenomena across volumes beyond current observational limits. Instruments such as JWST, Roman, ELT, SKA, Athena, CTA, LISA, and IceCube Gen 2, in combination with exascale simulations, will provide constraints on dark energy, dark matter, and the structure of the cosmic web in regions previously inaccessible to direct measurement.